Math Humans. We're going to do P3 today. We're going to be talking about functions and their graphs. Our specific objectives is that we're going to look at function notation, we're going to evaluate functions, we're going to talk about domain and range, and then we're going to talk about transformations. So I've pre-written some definitions just to go back and remember. The first one is that a relation is just a set of ordered pairs. A function is a unique relation where every y value has a unique x value, okay? And it passes the vertical line test. All right, sorry, my computer was being weird. All right, independent variable is always x. Remember that an independent variable means that you can't change it. The classic example is that is time. The dependent variable is y. That means that the outcome of y depends on what happens with x. Domain and range. Domain is the set of relevant x values. Range is the set of relevant y values. When we report domain and range, the expectation is that you're always going to use interval notation. Alrighty, so now we're ready to start in our first topic. That one's going to be, let's evaluate a function. So example number 1 is going to be evaluate. And our function is going to be f of x is equal to x squared plus 7. And I want to evaluate it. I want to do f of 3a, and then I want to do f of x plus delta x minus f of x over delta x. And then, of course, in this particular case, delta x can't equal 0 because then the world will explode. Remember that when you evaluate a function, this becomes the input, and this goes into everywhere there is a variable. So f of 3a is going to equal 3a, parentheses are good, plus 7. So this is 9a squared plus 7. So then I would write my conclusion statement. This is equal to 9a squared plus 7. So that one was pretty straightforward. To do the second one, I'm going to come up here because I need a little bit more room. When I do the second evaluation, if I do f of x plus delta x minus the original function all over delta x, and you're going to see this many times this year. So this is going to be x plus delta x quantity squared plus 7 minus, I ran out of room, x squared plus 7. And all of that is over delta x. And I need to put that guy in parentheses to make sure that I don't screw up my signs. So if you expand this, remember that if I have a plus b quantity squared, you square the first term, you multiply the insides together and double it, and you square the last term. So when I square this, I get x squared plus 2x delta x plus delta x squared plus 7 minus x squared minus 7 over delta x. So if we start to clean up the numerator, notice that the 7's cancel, notice that the x squareds cancel, and now I have an interesting situation, and I'm just going to show you to simplify. I'm going to factor out a delta x, and I get 2x plus delta x, and then it's divided by delta x. Now those delta x's cancel, and then my solution would be 2x plus delta x. I'm going to write my conclusion statement. Actually, I'll write it over here. So I would say f of x plus delta x minus f of x over the delta x is going to equal 2x plus delta x. And for right now, that doesn't have a lot of meaning. It will as the semester goes on. All right. The next thing I want to talk about is domain and range. And you've talked about this for a million years, but we will use this a lot this year, so we want to go back and review it. So remember that domain is the set of x values, and range is the set of y values. Domain is read left to right, and range is read bottom up. Okay, So let's just do an example. So for the second example, we're going to have the equation f of x is equal to 1 over x squared minus 4. This is a rational function. And remember, a rational function is a function divided by a function. So that might be f of x divided by g of x. And I want to find the domain and range. So I highly recommend that you factor. I also highly recommend that you sketch the graph. So this is going to factor, we'll do it down here, into x plus 2 and x minus 2 because it's a difference of two squares. Remember then that these are the vertical asymptotes because they are in the denominator. So I'm going to have vertical asymptotes at x is equal to plus or minus 2. Remember, you set the baby equations equal to 0 when you solve. Okay? Notice that my horizontal asymptote is going to happen at y is equal to 0 because the degree in the denominator is higher than the degree in the numerator, and we will review that later. So now I'm going to take this information and I'm going to put it onto a graph. So I have a vertical at a negative 2, and you always want to sketch your asymptotes. There's my other vertical, and then I always put an arrow going this way showing that's my horizontal asymptote. And then it's polite to use your grapher. And so my graph is going to look something like this, okay? And actually this doesn't touch, so crappy graphing, sorry. The domain, if I'm going from the left, is a negative infinity. That's the very most left point. And it stops at a negative 2, not included. It starts again from a negative 2 to 2, and then it starts again at 2 and goes to positive infinity. And then the range, and we would actually want to find this value right here, and we could do that. But I'm just going to tell you right now that that's going to be a negative 1/4. So my range is going to go from the bottom, negative infinity, to a negative 1/4, and that value is included. And then it's going to start again on the other side of the horizontal asymptote, and it's going to go from 0 to positive infinity. Alrighty? Let's do another one with domain and range. So the third one, our third example, your function is going to be f of x is equal to the square root of x minus 1. And again, I want to find the domain and the range. The graph is just the square root function that's been translated one unit to the right. So here's my handy dandy little graph. The domain is going to start at 1 and go to infinity. And if you substitute this value into the equation, the square root of 0 is 0. Remember that I can't take the square root of a negative because it doesn't show up on the real number plane. The range is going to start at 0 and it's going to go to positive infinity. All right, the next function that I want to talk about is a piecewise function, and we did some of these in pre-calc. They're really pretty entertaining. We will see them a lot in calculus. So remember that a piecewise function is a collection of pieces of different functions. Okay? For example, if I have f of x is equal to, and then I have 1 minus x, and x is going to be less than 1, and then I have the other piece is the square root of x minus 1, and x is greater than 1, okay? So if I want to graph this by hand, remember we did some of this last year, I would graph each piece and then erase where it's not defined, okay? And that's supposed to be a dot. So this is a negative x plus 1, so this particular graph is going to be a straight line. Its x-intercept is 1, and it's going to come into here, and this value is actually not included. Okay, so that is the top piece. The next one, the square root function, says that x is greater than 1, so again, the 1 is not included, and it would go that way. And so that would be my cute little piecewise. If you want to do these in your grapher, so you would go to your first equation and you would put the first function in parentheses divided by x is less than 1. And if you'll remember, let me bring in my handy dandy grapher to show you how to do that. I'm only going to put in You make sure that those are turned off, because remember, you can't graph anything with them on. So I'm going to enter the first one, and it is parentheses 1 minus x divided by its condition, so second math, and oops, except I forgot, so I'm going to go back. I have to put the x in there. So x, and now I can do my second test, is less than 1. And then I'm going to go ahead and just put the second equation in there. So this is parentheses second square root of x minus 1 outside close divided by open, and then I have to put in its condition and put in second test. He is greater than 1, 3, 1, close, zoom, 6. There's the left piece, and there's the right piece. So cool! All right, so that's how you graph a piecewise in your handy-dandy calculator. Cruising right along with all of these different topics that we talked about in pre-calc, one-to-one is the next thing that we want to talk about when we're talking about functions. Because remember, one-to-one was different if we were talking about logarithms. So a function is one-to-one. So I'm going to do this little guy because he is one-to-one. Notice that the graph y is equal to x cubed passes the vertical line test. So I'm going to write that it passes the vertical line test, and it passes, ooh, look at all those cool colors. It passes the horizontal line test, which means that the function is therefore one-to-one. So remember, those three little dots mean it is one-to-one. And when a function is one-to-one, that means that f is a function, and it means that the inverse of the graph is also a function. Okay? So that's what one-to-one means. And again, I'm sorry, we just get all of these different little topics. So now let's talk about the 8 basic. Sometimes they're called parent functions. And it's really important to remember what these look like, and we're going to talk about translations in just a moment, because 50% of your AP exam is without a calculator, and you need to be able to know what a graph looks like. The first one is y is equal to x, and it is just sometimes called the identity function. It looks like that. The next one is y is equal to x squared. It is our cute little parabola, and it is centered at the origin, and it looks like that. We just did x cubed, so I'll just sketch it again in case you had a brain fart. Looks like that. Okay, alrighty. The next one is y is equal to the square root of x. And notice that I only included the positive root, so that means it's only the top half of the curve. Because if I include the bottom half of the curve, this function is not one-to-one. The next one is y is equal to the absolute value of x. And it's really important that you know what this one looks like, because in calculus, this little guy presents some problems. And technically, it turns it into a piecewise function. And we will talk about this later in the semester as we cruise along. But it is important to remember what the graph of an absolute value looks like, because sometimes his little vertex creates problems. We'll talk about that later in the semester. The next one is y is equal to 1 over x. It is our rational function. I have vertical asymptotes at x is equal to 0, horizontal asymptotes at y is equal to 0. It is our first function that actually has asymptotes. The next of the 8 basic is the sine of x. Yeah, trig. We're going to do some trig, and hopefully you remember your trig. Remember, sine starts low, and it looks like this, and then it looks like that. That's just about a pathetic graph. The next one is y is equal to the cosine of x. Remember, cosine starts high, finishes high, and so cosine looks like that, so then it looks like that. Sorry. Woo! All right. So now let's talk about transformations. And again, if I'm trying to figure out what a graph looks like and I don't have access to my grapher, I need to be able to pull off a transformation. So we're going to say y is equal to f of x is the parent function, okay? So then if I have y is equal to f of x minus c, remember we talked about this last year. This is inside the function, and anything that's inside the function is opposite. So I'm going to write it over here. Inside equals opposite. Outside equals true. So that means it's the actual value that it is. So this is going to be right. Right is positive. Remember, it's the opposite, c. And then if I have y is equal to f of x plus c, that would be left c. If I have y is equal to f of x plus c, this is outside the function. Inside the function is horizontal. Outside the function is vertical. So some type of vertical change. So this is going to go up c. And if I had y is equal to f of x minus c, that would go down c. Okay, let me turn the page and we have some more. That was like a whole couple of days in pre-calc. If I have y is equal to a negative f of x outside the function, which is a vertical change, this is going to reflect across the x-axis, and we talked about this last year. So if I had a function that looks like this, and I reflected it across the x-axis, that is a vertical change because the graph changed vertically, okay, and that's outside the function. If I have y is equal to f of a negative x, that is inside the function, that is a horizontal change. So this is going to reflect across the y-axis. And then if I have y is equal to a negative f of a negative x, this is going to reflect around, slightly different word, the origin, okay? Alrighty, so I just want to write in our next example, I want to write an equation, and we're going to talk about the transformations. So the directions in my scribbled hieroglyphics say what are the transformations, and we're going to have y is equal to 3 sine, and then I'm going to have 2 x minus 5, and then plus 7. Remember when we talk about transformations, because we read left to right, we report math left to right. So this is going to be a vertical stretch of 3. It is going to be a horizontal shrink of 1/2. Inside the function is opposite. It is going to be a shift 5 to the right, opposite, and it's going to be up 7. Okay, so those would be the transformations to the regular function. All right, now we want to talk about polynomials. Okay, so the generic equation for a polynomial is a sub n x to the n plus, and then the next one x to the n minus 1 plus dot dot dot, and then you get a sub 2x squared plus a sub 1x plus a sub 0. And this is kind of the fancy math formula. But basically, all we really care about are some of the little details. N is equal to the degree, and it's always going to be the highest exponent. And remember that the degree of an equation does all kinds of things. It tells you what the shape of the curve is going to be. It tells you how many zeros you're going to have. So it tells you the shape of the curve, and it tells you how many x-intercepts or zeros. Okay. A sub I are the coefficients. The very first coefficient, a sub n, is called the leading coefficient, and that's going to be your vertical stretch or shrink. And then it's also going to be your reflection, if there is one, okay? And then a sub 0 is the constant, and that is going to be your y-intercept. All right, as we continue talking about polynomials, one of the things that we talked about in pre-calc was the leading coefficient test. And basically, it just helps you to decide what the graph is going to look like. So if I have a function, f of x is equal to a sub n, and x to an even power. Hang on, my computer decided that we had been going too long. There we go. Whew, minor little delay. If we have an even power and a sub n is positive, then my end behavior is going to be here and here. Alrighty, and we'll talk about the more efficient way of writing this later, but for right now this is sufficient. And then if a is negative, then that means that my end behavior is going to be down and down. The nicest way to think about this is y is equal to x squared. When it's positive, we know that it looks like this. And so then as x approaches negative infinity, the y's are approaching positive infinity, and as x approaches positive infinity, the y's are approaching positive infinity. But if I have the opposite situation and I have a reflection because a is negative, then as x approaches negative infinity, the y's approach, negative infinity, and as x approaches positive infinity, the y's also approach negative infinity. So it changes the end behavior of the graph. If, on the other hand, f of x is equal to a sub n and x is odd, right? The classic example is y is equal to x to the third, okay? If a sub n is greater than 0, then my end behavior is down and up. And if a sub n is less than 0, then my end behavior is going to be up and down. And I like to think about my parent function, okay? So this would be as x approaches negative infinity, the y's are approaching negative infinity. And as x approaches positive infinity, the y's are approaching positive infinity. So that is the standard. This is when a sub n is greater than 0. But if I do the opposite situation and I change and I make my graph go the other direction, then I would change these as well. As x approaches negative infinity, y approaches positive, and as x approaches positive infinity, y approaches negative infinity. And this would be if a sub n is negative. All right, we only have a little bit more to go. This is actually kind of long. All right, so I want to talk about combining functions, and I'm not going to do all of the examples because I think we'll remember that from previous math courses. So if I have f of x is equal to 2x minus 3 and g of x is equal to x squared plus 1, I could do math on my functions. So for example, I could do f of x plus g of x, and that would be pretty straightforward. I could do f of x minus g of x, and that would be pretty straightforward. Same thing, I can multiply the two functions together, and I can also divide the two functions. Hang on just a second, I'll move my paper so you can see. Okay, so those are all fairly straightforward from pre-calc. The one that I really need you to remember are the compositions. So if I wanted to do f of g of x, then that would be f of x squared plus 1. Remember that we start on the inside of the function. And now this becomes the input into this function. So that's 2 times x squared plus 1 minus 3. and then I would simplify. So 2x squared plus 2 minus 3 is equal to 2x squared minus 1. And that is the composition f of g of x. Remember that these two types of notation say the exact same thing. And then I could also do the composition in the reverse order. So I'll do f. I could do g of f of x, and that would be g of the 2x minus 3, which would be 2x minus 3 quantity squared plus 1, and then you would reduce that, which I'm sure that you can remember how to do. All right, almost done. So now I want to talk about even and odd functions. If you will remember, there is one test. If I want to determine whether a function is even or odd, I need to determine the symmetry. And so to determine symmetry, we run a negative x through the function. If I get the original function, then it is an even function, which also means it is symmetric about the y-axis. And if I ran a negative x through a function and all of the signs were the exact opposite, then that would be an odd function, which means it is symmetric about the origin. And again, the classic examples would be if I started with f of x is equal to x squared, and then I determined, and I ran a negative x through the function. This is a negative x quantity squared, and notice that I get the original function. That means that this particular function is symmetric about the y-axis. It also means that it is an even function. All of the signs have to be the same. And if I take the other one, so let's change and do another function, and let's do 1 plus the cosine of x. And if I run a negative x through the function, I get 1 plus the cosine of a negative x. So we need to think about this. If my cosine of a positive angle is here, then cosine of a negative is here. Notice that the cosines would stay the same. So then this would be 1 plus the cosine of x, because the cosines stay the same. So therefore, this would be an even function. And again, it would be symmetric about the origin. Okay? All right. That is it for today. That was a long video. Thank you for your patience, and I